below 10 in many cases. These are annual means. You can see the error bars around them. That includes all the changes that occur with floods, all those other things. And as I mentioned, I didn't think that heat had a lot to do with the story, because when you plot the average temperatures, the water doesn't really change heat content greatly as it moves through the system on an annual basis. You can see there's no relationship between distance from the midpoint and the temperature of the water. So that means we've got longitudinal organization in how these systems work. And if we start to tear it apart by looking at the individual surveys of these wells, we can see that the relationship is solid in autumn. During winter, again, oxygen declining, despite cold temperatures when biological activity may be low. In the spring, when flows are higher, same story. But in the summer, we lose that organization. It breaks down from a series of longitudinal patterns into something else, driven by something else. So there's reason to believe there's longitudinal organization and reason to believe that there are other forces at work. Well, this is a representation of the floodplain as a whole with all 19 wells. As I mentioned earlier, there are two distinct transects. What happens if we look at them independently? Here are the annual means again for the electrical conductivity increasing with distance down the floodplain and dissolved oxygen declining. We see that same pattern if we go far afield into the passive old growth environments. We see some remarkably tight relationships. This is across 5 kilometers distance and 5 seasons, and you've got an R squared of 0.9. Ecologists don't get R squared of 0.9. In order to get them, we have to use something like electrical conductivity. But this clearly suggests that there's some sort of